Imagine walking into a house where lights adjust automatically as you enter a room, the thermostat optimizes energy use, and your coffee machine starts brewing just before you wake up. That's smart home IoT in action. Now, take a farm where soil moisture sensors trigger pumps, and data from multiple fields flows to a dashboard for analytics. Finally, think about a factory floor where ESP32 sensors monitor machinery health, preventing costly breakdowns. In this lesson, we'll analyze these real-world IoT implementations, exploring components, challenges, and practical design choices. By the end, you'll understand how devices, connectivity, and cloud integration come together, and you'll gain actionable insights to design robust ESP32-based IoT systems yourself. Smart home projects illustrate how small ESP32 devices can automate daily life while remaining reliable and secure. For example, a motion sensor triggers a light relay, while a temperature sensor adjusts the HVAC system. Practical lessons include modular design, OTA updates, and encrypted communication to protect user data. Network reliability and protocol selection matter. Wi-Fi works well indoors, but BLE or ESP now can optimize energy and responsiveness for certain devices. In my experience, testing with a small setup before scaling prevents common pitfalls. Ask yourself, how will adding 10 more devices impact network traffic? Planning for scalability and troubleshooting upfront saves headaches later. IoT in agriculture shows the power of ESP32 for optimizing resources and monitoring crops remotely. Soil moisture sensors, temperature sensors, and actuators like water pumps can operate autonomously using MQTT or HTTP to communicate with dashboards. Key considerations include power management for remote nodes, choosing low-power protocols, and ensuring connectivity over large distances. In one farm project, implementing edge processing allowed the system to act locally even when internet connectivity dropped, while cloud dashboards provided trend analysis for decision-making. Reflect. What happens if one sensor node fails? Designing redundancy and fail-safe mechanisms is crucial for reliability in critical agricultural operations. Industrial IoT emphasizes monitoring, predictive maintenance, and real-time decision-making. ESP32 nodes equipped with vibration and temperature sensors can send alerts when thresholds exceed limits, preventing costly machine failures. Challenges include harsh environments, integration with legacy systems, and strict uptime requirements. Best practices involve using industrial-grade sensors, secure MQTT communication over TLS, and simulating high-load conditions before deployment. I've seen small bugs escalate quickly in factories. Early testing and robust logging are critical. Reflect on latency. Industrial environments often demand sub-second alerts, unlike home automation. This difference shapes architecture, protocol choice, and error handling strategies. Across smart homes, agriculture, and industrial automation, certain principles are universal. A solid IoT architecture, devices, connectivity, data, and application forms the foundation. Security, OTA updates, and protocol selection are non-negotiable, regardless of scale. Modular, small deployments allow testing and validation before full-scale rollout. Every project teaches practical trade-offs. Latency, power consumption, reliability, and maintainability must be balanced. Reflect. How does protocol choice differ for a BLE-based home device versus an MQTT-controlled factory machine? Understanding these decisions equips you to design ESP32 IoT systems that are robust, scalable, and practical. By analyzing these real-world IoT case studies, you gain actionable knowledge on system design, component selection, and deployment strategies. You now understand how smart homes, agricultural systems, and industrial automation differ and overlap, and how to approach architecture, connectivity, and security practically. Apply these insights to your ESP32 projects, plan for scalability, and anticipate operational challenges. This lesson equips you to make informed design choices, troubleshoot effectively, and build IoT systems that work reliably in diverse real-world scenarios.